Okay, well, welcome everyone to another TCS Plus talk. It is a great pleasure to have Yaonan from Columbia University. He's going to be speaking about first price auction is 1 minus 1 over e squared efficient. Just before we begin, I do want to encourage everyone to keep their cameras on. This will give Yaonan some visual feedback. It's always more enjoyable to give an online talk in this way. And encourage people to ask questions. You can just unmute yourself or can write it in the chat, and I'll be monitoring the chat. But after the talk, we'll kind of have a session to just hang out with Yaonan and discuss maybe open problems or anything that comes up during the talk. But with that being said, I think that gets everything out of the way. So Yaonan, please go ahead.
Oh, thank you for the introduction. Yeah, and thank you for coming to this talk. Today, I wanted to share two recent works of mine. One is very recent Fox 2022 paper. First price auction is 1 minus 1 over e squared efficient, which establishes the tight price of Anarchy for first price auction. The second work is a follow-up work called the price of stability for first price auction, which establishes the same tight price of stability bonds, also 1 minus 1 over e squared. To begin with, throughout this talk, we will consider the most classical auction scenario, single item auction problem. Here, suppose I am the auctioneer and I have an item to sell to one of n many bidders. Say I want to sell ice cream to one of C, Rocco, or Pian. And to formalize this model, here it is. The given is first, me as the auctioneer has a single indivisible item for sale, and there are n buyers. The buyers, we assume that they have private unknown values, but we do know, and every other participant, bidder, know all the value distributions. And for each bidder, his or her objective, you say, those bidders themselves are also rational. So they, by joining this auction, each of them would maximize his or her own utility. Utility, say, suppose she has a value of $10 for this ice cream, then of course he would like to purchase this item through lowest possible price. So the utility would be the difference between value and payment from the buyer, conditioned on that bidder wins in the auction. And the auction rule, in an auction, you can imagine it as an algorithm that the auctioneer calculates bids from the bidders and then determine the winner and the payments of the bidders. In the literature, there are two canonical optimization objectives. One is social welfare and the other is revenue. Social welfare, as the name suggests, it refers to the total happiness of all participants. Also, you can, with simple algebra, you can see that the social welfare is exactly the value of the winner. And revenue refers to the happiness of the auctioneer, that is the payment of the winner. And throughout this talk, we will concentrate on first price auction. Of course, the first price auction is the most prevalent and one of the most important auction since ancient. Its allocation and payment rule are truly simple. The allocation is that the highest bidder gets the item and all trust pays his or her own bid. and every other losing bidder gets nothing and pay nothing. Once again, we assume that the values are random variable drawn from some distribution. The outcome values and the outcome bits are unknown. I mean, private information transferred to every individual bidder, but the distributions from which those values and bits are drawn are public information. Again, the question of bidder in first price auction is I would like to maximize my utility by my expected utility by reporting a strategic bid. And you can easily say that, well, if I have a value of $10 for the item, I really will not, I prefer to bid a lower bid than $10. This is because if I have a lower bid, if I win, then I get a non-negative utility. But if I overbid than $10, even if I get the item, I can only get a negative utility. Yeah, this is what the model of first price auction. And to get familiar with this model, let's look at a simple example from Fakery's seminal work. Suppose we have two bidders, Alice and Bob. Each of them has a uniform random value from the 0-1 uniform distribution. And suppose that Alice bids half of her value. Then let's say what is the best strategy for Bob? Suppose Bob has a value of V2 and a bid of B2. Then the utility of Bob conditioned on winning would be the difference of his value and bid. And we consider the expectation, so we further multiply the winning probability. And with simple algebra, we can easily see that Bob maximizes his expected utility for whatever value of him, he bids half of his value. So this means that if Bob and Alice has the symmetric strategy, and that is each of them always bids half, and as a consequence, this is equilibrium in a sense that if Alice use this strategy, Bob cannot improve his own utility by modifying his own strategy. So it is for Bob. So another remarkable property of this example is that you see, because Alice and Bob use the symmetric strategy, bidding half of his or her value, the higher bidder between them must be the higher valuer. So the bidder who gets the winner of the first price auction is no longer not only the higher bidder but also the higher valuer. So this example is social welfare optimal. Okay, let's give the formal definition of Bayesian-Nash equilibrium. Bayesian-Nash equilibrium is a strategy is a randomized bid-to-value mapping. That is, provided an outcome value of mine, I would the random bid I would like to use. And Nash equilibrium means it almost says the best response condition. That is, for every single bidder, condition over the randomness of others' value strategy, and by using my considered strategy, my utility will be maximized. And for simplicity, we will use BNE, this notation, to denote the space of our equilibrium for a given value distribution.
I have a question.
Yeah.
So does it, do people also consider when you don't know other people's strategies?
Very, very good question. Yeah. how to say? You can assume that everyone know other people's strategy. For example, consider this example. Even if Alice claims to Bob that, well, my value is uniform random between 0 and 1, and my strategy, I promise that my strategy is beating half of my value, then this is still an equilibrium, right? Okay. Thank you. Thank you for the question. Okay, and we will another two concepts we will consider in this talk is our price of anarchy and price of stability. You say the OPT refers the optimal social welfare refers to the benchmark. That is, you say if a first price auction like our previous example, it is social welfare optimal, and this means this example is perfectly efficient. The other, and for value distribution and equilibrium, we also will consider the expected auction social welfare from this equilibrium. And the price of anarchy and the price of stability refers to the minimum possible welfare guarantee under equilibrium. The difference is that some of you might have heard that a game may have multiple equilibrium, and the price of anarchy always considers the welfare best equilibrium, and the POS considers the worst best equilibrium. POA considers the worst equilibrium. And by definition, you can see that POA is bounded from above by POS, and each of them is at most 100. So with our formal language, let's take a first look at our previous example. We have seen that with IID uniform 0, 1 uniform random value, we know that Bayesian equilibrium always exists. Also, POA and POS are 100%. Actually, both observations can be generalized to arbitrary IID. I mean, in our previous example, we just consider two filters, and they are IID uniform values. Actually, even for an arbitrary number of bidders, as long as they have IID value, not necessarily uniform, Bayesian equilibrium always exists and is unique. Also, these equilibrium have the property that higher bidder must be the higher valuer, so POA and POS both are 100%. But if we consider asymmetric values, each of the two properties, existence and uniqueness of Bayesian equilibrium and POA POS are 100%. Both properties not necessarily hold. First, look at this example. Suppose Alice has a fixed value of 1. Bob has a fixed value of 0. Then another is to erase, that is the underlying tie-breaking rule. You say Bob has a value of 0, then imagine that he also would like to bid 0. Then what's the best strategy for Alice? If we use the 50-50 tie-breaking rule, then there will be no equilibrium, because as this figure shows, Alice, when she decreases her bid from 1 gradually until a 0 bid, then for any non-zero bid, she gets a higher and a higher bid. But if her bid is exactly 0, then her winning probability will not be approximately 1, but will be half. So that means this curve is the utility function of Alice's bid. So there is no max. This function has a supremum, but has no maximum. So there, under this 50-50 type rating rule, Alice has this game has no exact equilibrium, but it has an approximate equilibrium. That is, Alice has a bit close to 0, but not exactly. But if we consider the favor Alice type rating rule, that this point at half move is lifted to 1, then say under the new type rating rule, there exists exact equilibrium. This example is slightly different from our knowledge that Nash proves that every finite game admits exact Nash equilibrium. This is because you see here we are considering a infinite game because the strategy space can be any real number between 0 and 1, and there are infinite. That means there are infinite number of strategies of actions. Okay, and let's look at the third example. In this example, Alice say she has a value of 1 and Bob has a uniform random value between 0 and 1. Actually, this example has infinitely many Nash equilibrium, and I would just present the simplest equilibrium. This equilibrium says that well, Alice also she has a deterministic value of 1. She still has a randomized strategy, and her random bit follows this distribution B1 given by this CDF. Bob, he has a uniform random bit value, and he has a deterministic strategy. That is, his strategy is just a deterministic function of his value given by this formula. And the important thing of this example is that its POA is bounded away from 100%. For example, suppose Bob has a value of 3/4. Then 3/4 would be here. And if you look at the point corresponding to 3/4 value, then you can, with simple algebra, you can see that the beta of Bob would be 2/3, and 2/3 corresponding to 55% chance of winning. So that means also Bob, his value of 3/4 is not optimal, less than Alice, her value of 1, but Bob wins with a non-zero probability. So this example is POA is not 100%. Okay, to summarize, POA refers to the worst case equilibrium and the worst case guarantee, social welfare guarantee. POS considers the guarantee under the best case equilibrium. The difference between symmetric versus asymmetric values is that first, the existence and uniqueness of equilibrium becomes an issue, and it depends on the underlying type rating rules. Also, you say, since the existence of equilibrium becomes a problem, since we have the concern that whether the concept of price of anarchy and stability are still widely applicable. Also, the POA and POS are less than 100%, and we may worry about whether they will be too small. That is, the efficiency of first price auction is not good enough. Okay, let me summarize the previous works. The previous canonical approach for price of anarchy in auctions is the smoothness framework by Tim Roughgarden in this seminal paper. And later, specifically for first price auction, in this stock 13 work facilitates and advertises generalize the preference smoothness framework from non-Bayesian setting to Bayesian setting. And for the first time, they prove a bound of 1 minus 1 over E for POA of first price auction. Later in this stock 18 paper, Tagat and Zihe Wang, they incorporate extra independence arguments into the smoothness framework and improve the welfare guarantee. And from the other side, these three works construct worse and worse instances. And before our work, the best known impossibility bound for POA would be this number. But from the other, the progress on price of stability remains a huge blank. Nothing is known except implications from POA. Possibly this is because that you say POA considers the worst case value distribution and the worst case equilibrium. So this is a minimization problem. In contrast, POS considers the worst case value distribution, but the best case equilibrium. So this is a minimax optimization and might be harder than minimization problem. Also, as mentioned, the problem of the existence of equilibrium becomes a problem. So we worry about whether the concept of POA and POS are widely applicable. Also, I need to mention that also the proofs based on smoothness are non-constructive proofs. In our work, we propose a completely different framework. Roughly speaking, and this framework enables constructive proofs and gives more information about Bayesian-Nash equilibrium. Roughly speaking, our framework has three parts. First, we will switching our viewpoint of Bayesian-Nash equilibrium, and that is, we will give a new characterization for equilibrium and our problem. And this similar idea has appeared in these three and other previous works. The second step would be, well, after this switching viewpoint step, our original optimization problem will become a easier optimization problem, and this helps us to give a constructive proof that directly characterizes the worst case for Bayesian for POA, and the third step would be, well, using this worst case instance for POA, we slightly perturb it and present a more extra uniqueness of equilibrium arguments, and as a consequence, we will show that POS are the same as the POA, and so we will establish this theorem. Another interesting thing is that our whole framework is constructive. So we will introduce another concept called infinitesimally approximate equilibrium. You can imagine it as the closure of the original exact equilibrium space. And this new actually POA and POS 1 minus 1 over E square holds not only for the original exact equilibrium, but also infinitesimally approximate equilibrium. So this makes and the approximate equilibrium always exists and relies not on the underlying tie-breaking rule. So this makes our framework more universal and robust. I must actually the second and the third parts are very technical. So in this talk, I will concentrate more on the first step, switching viewpoints.
So I have a question.
Yeah.
I am sorry, I didn't understand. So what kind of, so a game is defined by the valuation distributions. And what is the game for which POA is equal to POS equal to 1 by 1 minus E square? What are the kind of games for which this is true, that POA is equal, like what are the games for which the theorem holds? I might have missed it.
Okay. You say the original okay.
So given
This,
yes, yeah.
For a given value distribution, this notation is not rigorous. The more rigorous one would be it's a space depending on the value distribution weight, also on the underlying type ranking rule. Yeah, but if the type ranking rule is very weird, then this space of equilibrium possibly is empty. So if this is the case, then for this specific value distribution, because the equilibrium space is empty, the concept of POA and POS are not that suitable.
Yeah.
But we actually prove that we can steadily expand the space of equilibrium. You can imagine as the closure of the original space. And this always guarantees the existence of equilibrium or approximate equilibrium. Then this space always will not be empty and makes the concept of POA and POS more suitable. Okay.
Okay, and then for those kind of problems, you prove that POA is equal to POS equal to 1 minus 1 B squared.
Yes, exactly. Okay, thank you. Okay. To begin with, let's remind some very familiar concepts about the switching viewpoints. First is linear programming. You say the strong duality theorem tells us that the optimal objective to the original to the primal LP is the same as the solution to the dual LP. Also, Fourier transform tells us that the average energy of the untransformed function is the same as the average energy of the transformed function. So on and so forth, we have tons of such examples. And the idea here is similar. By the way, I wonder how many of you are working on AGT and how many of you have heard of the revenue equivalence theorem by Meyerson? Okay, no worries. Then maybe I should directly introduce the current work. The current work, roughly speaking, you say the original definition of Bayesian equilibrium almost says that the strategy is the best response for value distribution, right? And our idea, the first step of our work will be a new characterization of equilibrium based on gates. And the benefit of this new characterization is that you say our previous optimization problem is the search space is the product of two infinite sets. First is we need to consider all value distribution, and for every single value distribution, we need to consider all Bayesian equilibrium. And as mentioned, for a given value distribution, possibly there are infinitely many equilibria. So preference search space is very complicated. But after this transformation, our new search space will not be the product of two sets, but just a single infinite sets. Still complicated, but already much easier than the previous one, because roughly, you can imagine that we reduce the dimension of our search space by infinite. But the other thing is that you say the preference search space is all well-defined value distribution and all corresponding equilibrium, but it's actually not all corresponding bid distributions are in our search space. Only those valid or those equilibrium bid distributions will be our considered new search space. Validity will be a technical condition, and I will elaborate on what this condition stands for. Also, here I mentioned an earlier work of mine because the similar idea, that is transform a more complicated optimization problem into a still complicated but relatively easier problem. The similar idea appears in an earlier work of mine. The difference is that the earlier work we can immediately apply the revenue equivalence theorem by Meyerson, a well-known structural result to get such a transformation. But in this work, there is no existing tool, and we must build this structure and transform the original problem to the new one by we must develop a tool by ourselves. Okay. To introduce this new characterization, first we need to consider bid distribution. You see, by now we always consider independent value distribution, and we always consider a single person's strategy only depends on his or her own value, but not on other people's values. So the corresponding bid distribution also form a product distribution. Also, I will use the be valid, this notation to denote all equilibrium bid distributions that can be resulted from one value distribution and equilibrium thereof. Another important thing is bid to value mappings. Given by this formula, you may think it's complicated, but soon after I will explain how can we derive this formula. And roughly speaking, our new characterization is that bid distribution is valid. That is, it corresponds to a specific equilibrium if and only if first condition that the support union of all bid distribution is a single interval between some gamma and some lambda. It cannot be the union of two or more disconnected intervals, but must be a single one. The second condition is that the bid to value mappings are weak increasing functions over this bid supports. Also, this is the informal version. The formal version addresses other technical issues, and actually this new characterization is very general. Only these bid to value mappings are specific to first price auction. But the other ideas can be applied to other auctions and future works. Okay, let's say how to derive this bid to value mapping specifically for first price auction. You say in first price auction, the previous concept or condition for equilibrium is the best response. So we need to consider for every single bidder I, how likely his or her winning probability. It is the product of you say first price auction. So the winning probability is exactly how likely every other people has a lower bid. So it's the product of other CBFs. And the expected utility of this bidder on a value of V and a bid of B would be the difference times the winning probability. And the best response, this condition essentially means the considered bid must be a maximizer for this utility formula. And so making this derivative to be zero, and with simple algebra, we can get this bid to value mapping formula. Okay, and emphasize again, you say only the whole framework is very general. You say the essential part is only the best response condition and take a derivative, but only the only thing specific to first price auction is the formula is the utility formula. And for example, maybe some of you have heard of the all-pay auction. And for all-pay auction, we will derive a different formula in this term. Okay. Okay, then let's summarize the advantage of our new characterization for Bayesian based on bids. You say the previous value strategy-based statement for equilibrium. First, you say best response is a very abstract condition. It's we can hardly say something about it. Second, one value distribution, the number of equilibrium of it's uncertain. And depends on the underlying type breaking rule. Possibly there is no equilibrium, possibly one unique equilibrium, and possibly infinitely many equilibrium. Also, how to calculate one equilibrium from a given value distribution, this is very well known. It is a well-known open problem, and this calculation is non-analytic. But our new characterization addresses all these three issues. First, compared to best response, monotonicity of bid to value mapping is very easy to understand condition, and we can using monotonicity, it's easier to develop more suitable techniques. Second, you say, as this imagine shows, the previous one value distribution possibly corresponds to a single equilibrium. Possibly it corresponds to multiple equilibrium, but now it's easier. Every single equilibrium, it always corresponds to a pair of value distribution and equilibrium thereof. Also, this construction is analytic and truly simple, just this identity. That means using a given bid distribution, we can using this formula, we can reconstruct the value distribution and reconstruct the equilibrium. And as mentioned, this greatly simplifies our optimization problem. We no longer consider the product of two infinite sets, but just consider a single infinite sets. Okay, but to complement this framework, we also need to develop the formulas for auction social welfare and optimal social welfare. Roughly speaking, these two formulas are given here. It's easy to understand. First, you say in first price auction, phi I refers to bid to value mapping, so it essentially means value. So this term means how much contribute the bid I conditional on a given bid, a specific bid B can contribute to auction. And this second term refers to the how likely it is the bid I who contribute the auction social welfare, and the last term refers to the density, the probability density. And the third and this term is also easy to understand. You say the integral of 1 minus the product of some distribution is exactly the expectation of the maximal value or among n many values. And this term is exactly the CDF of how likely that a beta I his or her value is at most a value of V. So using these two formulas together with our new characterization of equilibrium, we transform the previous problem given here, the original definition of POA, into a new definition. And roughly speaking, the main technical part of our work is to give a constructive proof and characterize the worst case for this new optimization problem. The high level, the detailed techniques are very complicated, so I would just give the high level idea. Roughly speaking, this constructive proof globally is that for a given bit distribution, the overall target is to show a specific bit distribution is the worst case, and as a consequence, that bit distribution is POA is exactly 1 minus 1 over E squared. And locally, our reduction, our constructive proof takes this way. For a given bit distribution, we need to construct more well-structured bit distribution, and to show that the new POA is smaller than the previous POA, and since along the way, along this way, the considered bit distribution will be more and more well-structured, and eventually it exactly becomes the target bit distribution B star. Okay. The other thing I need to also the whole proof is complicated. I would just briefly talk about one specific step, that is discretization scheme for equilibrium. This equilibrium is a famous hard to deal with concepts, and our work gives the first discretization scheme for equilibrium. This scheme would be very useful for future works such as computational complexity or learnability of Bayesian-Nash equilibrium. And if you are interested, I can give more details after the talk, or as more technical details. Along this way, we will prove that the tight POA for first price auction is exactly 1 minus 1 over E squared. And in the follow-up work, our soda paper, we, roughly speaking, we will modify the worst case for POA, and how to say, okay, the POA was the case. Actually, that instance has infinitely many equilibrium. So that instance also its POA is 1 minus 1 over E squared, but its POS is actually 100%. And the contribution of our follow-up soda paper is to modify that instance and present extra uniqueness of equilibrium technique. And then we will show that for the modified instance, not only POA is 1 minus 1 over E squared, but also POS are the same bound. Another thing is that you say different from the previous smoothness framework, which is non-constructive. Our new framework is wholly constructive. As mentioned, if the underlying type-breaking rule is very strange, then the existence of equilibrium also becomes a problem. Possibly, similar to the second figure, there is no equilibrium, and possibly similar to the last figure, the space of equilibrium is a closed set. And we will introduce the concept of infinitesimally approximate equilibrium. You can imagine it as the closure of the original equilibrium space. So we will always get the last figure type of space, a closed set. That's exactly what we want, because such a space guarantees the existence of equilibrium and makes the concept of POA and POS more robust and universal. Yeah, this is the formal statement of our adaptability statement theorem, and our work leaves many interesting directions for future work. First, the current POS paper is unfinished, and future versions will include more results. Also, you say our framework is very general, so it's likely to be applied to other auctions, say OP auction, generalized first or second price auction, and so on and so forth. The other interesting thing is that you say throughout this talk, we always consider the one optimization objective, that is social welfare. The other interesting thing will be the revenue guarantee of first price auction or other non-truthful auction. So it's interesting to prove the tighter revenue POA and POS for first price auction or other auctions. For such works, you can refer to these two works. Also, you say our framework is presents constructive proofs. So along this way, the structural results should be very helpful to other research aspects of equilibrium. I mean, especially computational complexity and learnability. Yeah, that's all.
Okay. Thanks, Yaonan, for this talk. I promised that I would take us offline and we can hang out and ask questions there. So I'll stop the recording now.